So in the last class, basically we discussed about how images are acquired using different devices, imaging devices. So the basic principle was that there has to be some energy source with appropriate wavelength, which will illuminate the object, and the reflected light rays or uh, source will be basically captured by some imaging system. And we discussed that for different sizes of the object we need to have different types of electromagnetic modality. And we also talked about the basic elements in a basic imaging device like camera. So first of all, we need to have an aperture which will limit the amount of light, because if we don't have aperture, we basically if an object is there, let us say some object, if if we don't have aperture, the light rays will be incidentting in all directions, so there will be no control over it. So the image that will be formed will be totally blurry or meaningless kind of thing. So aperture, what it basically helps to restrict the light rays which will be incident at particular angle only. And then there is a lens system which helps us to which helps the rays to get focused on the imaging surface, which is kept at the focal length of the lens. And then there is a photosensitive surface which basically gets excited. So we also discuss about the basic geometry of the camera optics. So if you assume there is a kind of a pinhole model, then we can have a relationship between scene coordinate. So a point in a scene coordinate where exactly it will form on the image coordinate, that can be obtained based on the, so if this is Z and this is the focal length, then we can have this relationship, this simple relationship using similar triangle. So also we discuss about this basic photometric model, that the intensity value that will be measured can be represented as a simple multiplication of the intensity of the illumination as well as the reflectance of that point. And in digital cameras, generally we have some kind of a light sensitive diode which converts the photons to electrons and accordingly generate some voltage output. And this is what we said, that different devices will have different arrangement of the sensors. So in normal digital cameras we'll have a 2D sensors. In scanners we have just a 1D strip of sensors, but it is combined with a linear mechanical motion to capture the entire surface. And in some advanced medical imaging devices like MRIs, we have multiple motions. We have the object moving inside the circular ring, and the circular ring itself will be rotating in. So by combination of the mechanical motion as well as the arrangement of the sensor arrays, we can acquire either 2D or the 3D surface of the object that has to be imaged. And as you asked last time, how do color? So this, if we just have a same sensor all over the place, then they are only going to get the basic achromatic light, or basically grayscale images. But to get color images, normally what is done, different sensor chips, they are basically um, coated with, or they are applied some kind of a color filter. So normally there are three color filters which are applied: red, green and blue, because in our eyes there are, as we said, there are two types of sensors which are called cones and rods. Cones are responsible uh, for color perception. So cones also, we will find that there are three types of cones in there. one which are majorly sensitive to red light or red spectrum of the wavelength of the light, and then there are other which are sensitive to green, and then there are few which are sensitive to blue. The majority ones are greens. The almost 70 to 80% of the cones are sensitive to green, few are to reds, and few are towards the blue. So to mimic that, the same thing is done in normal in all color cameras also. Different sensor, different pixel sensors, uh, individual sensors, they are coated with different color filters which will allow only that particular wavelength light to pass. So and then they are arranged, instead of having every pixel having all three filters, normally virtually all cameras have this kind of an arrangement which is called bare array arrangement. So there if you see majority one are green filters, majority of them are basically green filters, few of them are red, and few of them are blue. So there is a pattern of green blue, and then green no green red, and then green blue in this direction. So that is again because as we said, green are the maximum cones which are there in our eyes, they are sensitive to green light. So majority of the filters are actually green, and then the other portion of the things are, they are just approximated, so they don't so for example, this one will only this particular sensor will only going to give the intensity corresponding to the green light, and the other the blue and the red part is approximated from the adjacent neighboring values. So there is some kind of approximation which is done to produce a color image. So we'll talk about that about colors in later on when we discuss about color image processing. Discuss more into details about different color models, and how by a combination of RGB. So one most common model which is used is RGB model, because it is found that by combining these are called primary colors, by combining this red, green, and blue color, you can produce majority of all different shades of colors. Not all possible colors, but majority of the shades of the colors can be obtained by appropriate combination of weightage of proportion of these RGB colors. So that we'll discuss later on. So as we said, we are going to discuss digital images, because in our computer we are going to actually represent only digital images. So analog images generally are converted to digital images. If you have already captured an analog image, then there has to be some kind of a digitization thing. Earlier we used to have a firewire and all those things. Nowadays, as we said, we generally capture with digital image, digital camera itself. So in the digital camera itself, there is a either because the sensors are already individual sensors, so already there is a digitization happening because of the arrangement of the sensor pixels, or there is an ADC converter, analog to digital converter, there in the camera. So there is two things when we talk about digitization. One is called sampling and other is called quantization. So what these two terms mean, or the definition is written here. So, uh, sampling refers to the spatial part, and quantization refers to the intensity measurement. So, as we said, the actual image, seen image, will not be able to measure intensity values at every possible locations. Instead of measuring at every possible locations, we'll measure at regular intervals. So our entire grid can be divided uh, into samples which are distributed at regular intervals. So kind of a 2D grid here. So this kind of image will then actually appear. Will be only measuring. So this particular will this particular this all location in this are going to have just only one intensity value, whereas in actual this may have different possible intensity values, but within this one grid we are going to just record one intensity value. So that is what we are saying. We are measuring the image at only this finite number of points, and also the intensity values also instead of all real values ranging from 0 to some value, we'll be measuring at some discrete intensity values. So this is what is represented as, if you can see here, we are representing them with some discrete levels of intensity values, and that is basically called quantization. So this is just an illustration of that. If you draw this, if you go through this line AB on this image, if you measure the intensity values, the actual intensity values will look something like this. So initially they are all white, then towards going towards dark, and if you see there is a noise, this random thing is kind of a noise. So no intensity values will be just, there will be always some noise values, some fluctuations will be there. So sampling basically means that you will be measuring these the intensity values along this line A B in this image at only these particular intensity values at these particular locations, spatial locations. And quantization means whatever the intensity values will be here, you will be representing only by these different levels, intensity levels. So that will depend on how you store these intensity values, how many bits you use to store these intensity values. So if you use 8 bits, for example, how many levels we can have? If you are storing only positive values, let us say positive values. So what how many levels you can have with 8 bits? 2 to power 8. So with 8 bits we can have 2 to power 8 things. So if we are only storing positive values, then we can store values from 0 to 255. And if you are storing in if you want to also store negative values in 2's complement, we will have from minus 127 to 126. Okay, so can you quantize this? Just a simple thing. Let us say we are having these intensity values at different grid locations, and we will wherever we have to do a round off, we will take the floor value. So we'll round down, and we have to fix the clipping points are 0 to 5. So every value less than 0 will be put to 0, and every value greater than 5 will be put to 5. And we are having 6 levels. So what will be the values here? Quantization. So here there will be what will be here? And so on. Hopefully, this will be 3, 0, and so on. Hmm? So we can also represent images as functions. When we are saying digital image, that means we can represent images as digital function. What is a digital function? What is a discrete function? So normally a function ranges from one particular set of values to another particular set of values. So will be called domain, and the set of values here will be called range. So if both range and domain are continuous values, then we call this as a continuous function. If only the domain is discrete, whereas the range is continuous, we call it as a discrete function. And if both range and domain set values are discrete, we call it a digital function. So when we are saying digital image, that here, because we call it as digital image, because here both the domain values as well as the range values are all discrete values, because we are sampling both in the spatial domain. So these are our spatial coordinates. They will be taking some intensity value. So both the intensity and the spatial coordinates will be discrete values. So that's why we say our images are digital image, because we can represent them using a digital function. So it will be a mapping from we can say it is a mapping from R square to R, but in practically it will have some finite range values. So just as illustration, so let us say this particular sub image taken from some images. Let us say in this direction, along the horizontal direction we have x axis, and along the vertical direction we have a y axis, and the values of the spatial location from in x direction starts from 10 to 210, and y here starts from 15 to 165, and the intensity values are quantized from level 0 to 10. So what will be the range of x here? Hmm? So x is going from 10 to 210, y is going from 15 to 165, and the range is going from 0 to 10. So this is a, we can say this is a, we can represent this image by using by in terms of if you want to have a notation of a function, we'll have to say this is a this kind of a notation function. For color images, normally we'll have three different channels. What we say, instead of just one intensity value at every location, we'll have three intensity values which will refer to red channel, green channel, and blue channel. So in terms of function, we can say it's just a vector which where the red channel is stacked over green channel and blue channel. So we'll have three samples per pixel location. So one sample location is called one pixel, which is a short form of picture element. It is commonly known as pixel. For most of the course, will the most of the techniques that we'll be discussing will be talking about gray level images, but we'll see they can be straightforwardly applied to a color image, because color image is nothing but just a grayscale image with three different channels. So whatever we want, whatever techniques, so let us say we want to do some averaging operation here, we can do the same averaging by applying that averaging operation on each channel separately. So we'll talk about that later on. So if you are to write a color image in terms of a digital function, which of these notations are correct? So let us say there is a color image which has both all the three RGB component, which is made up of three channels. One is red channel, another is green, and the third one is blue channel. So which of these notations are will be correct for this, for denoting a color image? The first one is not. Hmm? What about second? Hmm? What about second? Yes or no? Huh? So the range will have what? So the domain will have what? X comma y. So whether it is color image or grayscale image, the x and y, there are only two dimensions. So we'll have r cross r here, and there are three values here. So this seems to be correct. Huh? So the domain is basically what are the, so see this will be divided into x and y locations, isn't it? So so the domain set will have x comma y values. So that's why we'll have two sets here, r cross r, and the range will have three values, red, green, and blue. So we have r cube here, and the other way to write this is r cross r cross r. So both second and fourth options are equivalent to write it. From our implementation perspective, when we are going to implement images in our, or when we are going to manipulate our images, we will, it's most convenient to see images as matrices, a 2D matrix. So most of the image processing platforms, libraries, they represent images as matrix. That is the most common representation. Either you are using MATLAB or Python, OpenCV, whatever. So images are represented as a two-dimensional matrix. A grayscale image, a 3D color image will be represented as a 3D matrix. So normally the convention is the leftmost column, the leftmost. So the horizontal. Uh, so the rows and columns, there will be rows and columns in this 2D matrix. So one of them is represented by Y, and another one is represented by X. And generally the leftmost column, the topmost and the leftmost pixel is basically uh, represented as 0 comma 0 and also referred as origin. When we talk of origin, we'll generally refer to this topmost pixel value. This. So you may start it from 0, you may start it from 1. Index can start from 1 also. That depends again on the library and the convention. But again, the indexes are very straightforward, like a 2D matrix. And we can, if you want to see any pixel value here, basically we just have to know the indexes of the x and y index, I comma j, and we will get the particular will be able to retrieve or change the value at that particular pixel of the image. So also 0, most times 0 refers to black value and 255 refers to white value in a normal image when you are using 8-bit representation. Sometimes it is also convenient to visualize images in this way, where the intensity is visualized as the third dimension. The another important concept about images is about its resolution. So whenever we specify an image, we also specify its resolution. Resolution can be in 3 dimensions. One dimension is your spatial resolution. The other resolution is in terms of intensity resolution. And third is when we are using videos, there is a temporal resolution also. And resolution will basically specify how close our digital image is to the actual scene image. So remember, when we are digitizing, we are actually losing some information. We are only measuring discrete values. So a digital image is going to just be an approximation of the real image or the real scene point. So how good our spatial and intensity resolution is there, that will determine how close our digital image is to the actual scene image. So what it actually means, so let us talk about these three resolution little bit. So spatial resolution basically refers to the is dependent on how the sampling was carried out. So how closely we have performed the sampling. So if you have performed sampling very finally, we'll have a higher spatial resolution, and if we have performed sampling sparsely, we'll have a low spatial resolution. And that will also affect in how much of the detail we can see in an image. So for a particular area, so these are the different spatial resolutions image of a particular image captured in a digital image. So you can see this one has low spatial resolution. We call this as a low spatial resolution, probably because the sampling was carried out sparsely. So we can see the details are not at all visible. Whereas this one on towards the other extreme has higher spatial resolution. So even if you zoom in, for example, we will be able to see more of the details in the image. An example, I think I don't have that image, but for this image, so this has around 1024 by 1024 pixels. This has 512 by 512 and so on. So this is the 1024 by 1024. This is the 512 by 512. Just resized it to this is to just to show how you are losing the information. So this is the smallest one, I think 32 by 32 one. So the same image 32 by 32, if you are now, if you are looking at in the same canvas of 1024 by 1024, the intensity values are only these many intensity values are have been captured. So you can see the details will be very much less visible, or we can only have an overall idea about what is there in this image. Whereas on the contrary, in this image, the details are much more visible, because the sampling was carried out at close spatial things. So there are many more number of pixels here which have uh, intensity values. So John, normally when we talk of a spatial resolution of a camera, we specify its in terms of its number of pixels. So we specify this camera has 1 megapixel resolution, or this camera has 10 megapixel resolution, and we think that the one which has higher resolution, higher pixels, has a higher resolution. So can you increase the spatial resolution if you just replicate the pixels? So for example, this image, if you just replicate this pixels at every row, every row and every column, if you replicate, can you get this image, which is just the next higher level replicating? So take the first column, and in the next column add just replicate the so the previous column, and then take the next other column, replicate it. So for example, if you are, I'm saying, let us say if you have 32 by, sorry, if you have a 32 by 32 pixel image, and we want next higher resolution, which is 64 by 64. So to resize this 32 by 32 to 64 by 64, we can just replicate every row and every column to get this. So will that be same image as the actual 64 by 64 image? No, no, because we are, so that means just specifying the number of pixels doesn't means you have a higher spatial resolution. It actually depends how the images was acquired at the time of capturing the things. So how much portion of the image, how much portion of the scene was corresponded to how many pixels in the actual camera. So intensity, of course, we have also already talked about this. So that depends on the quantization aspect that we said. So sampling was spatial, quantization is in terms of the intensity value. So the intensity resolution or quantization will depends on the number of bits that you may be using to store the image. So if you are using only one bit to store the image, you can only have a binary image. You can either store 0 or 1 value. If you are having 2 bits, you can store at least 4 different levels, and so on. Normally we have 8-bit image which stores 256, and then a 60 bits can store much higher resolution intensity levels. So again, that will also impact the fineness of the level of the details that you can discern in an image. So an illustration of this is shown in this image. Probably it's kind of a medical image. थोड़ा डरावनी image है, but it's so this is a image which has only one bit. So we can see there are only two levels here, either 0 or 1 black. And this, as we move towards the higher level, when we're using 8 bits pixel, we have at least this image has at least 256 different grade levels. And you can see the details getting lost as we move from 256 to only 2 levels. Most you can see some kind of a, so as you can see here, for example, in this image it is more very clear. So there is some kind of a circular artifact or that is appearing here. So because all these levels initially which were fine, now they are all grouped to only one intensity level, and then this set of intensity levels, they are now mapped to only just one single intensity level. So we can find this level of things getting reduced. So many times we do have to convert a grace level image to a binary image, where we'll see later on when we have to segment out a region of interest from the background. So where we just want two levels, a background region and a foreground region. So generally there we do some kind of a binarization. We take a gray level value, grayscale image, and we do a thresholding or some kind of operation to convert it into a binary image. And when there is a video, which is basically nothing but a sequence of images, we have a third dimension along the time axis. So we can have a resolution along the time. So that is what we are calling as temporal resolution. So video is basically not. So when we see a video is on a device, it's nothing but images sequences are being changed rapidly. So our eyes, they have only a uh, we cannot resolve more than 15 frames per second. So if something is changed at a higher rate than 15 frames per second, we see it as a continuous motion. So similarly, all cameras, they have a specification called frame rate. So frame rate will determine basically the amount of resolution that you can have in the time axis. So normal camera generally have 30 frames per second frame rate, because normal movies and videos, TV videos, basically they are played at this frame per second. Although our eyes can only see, uh, so beyond 15, anything will be appearing as a continuous motion to us. But say, for example, for specific applications, normally we have special cameras which have a higher frame rate. So for slow motion capturing cameras, we have 100 frames per second or beyond that. So if you want to capture slow motion sequence in action movies and all that, they use those kind of cameras to do that. So the question is, I'll talk about this. So later on, when we come to some numerical problem about the size of a videos thing. But one question generally which you, while if you have to purchasing a camera, or if you are using an image for some particular application, generally you have to specify, you have to decide how much resolution is sufficient for that. So so it all depends on the application, what you want to do with that particular image. So accordingly, you may have to choose a camera which, so normally if you increase the resolution, the cost will increase. The cost of the camera or the system setup, even computation cost, even memory requirement will increase. So and if you don't have sufficient resolution, then you won't get sufficient information to process. So you have to have some kind of a trade-off. So that depends on the need. So whether the image is looking aesthetically pleasing, or that depends on the application. So for example, if you are designing a traffic surveillance related application, so now these two images are of different spatial resolution. Now this, if you are interested in reading the the number plate, then this image is useless for us. We'll have to have images of higher resolution than this or higher to be able to recognize the numbers. Whereas if we are only interested in counting the number of cars or vehicles moving and the things, then even this resolution image is sufficient. We should not, in that case, we should not go for a high resolution, because we'll be unnecessary wasting our computation and memory on processing a high resolution image. So that we can suffice, this resolution images can suffice. So that resolution will depend on the requirements of the application. So again, three different images with three different levels of details. So if you are capturing a crowd image, probably you need a high resolution camera. Whereas if you are only capturing a face of a person, you can, even a low resolution camera should be sufficient. So some simple numerical exercise from the back of the book of your Gonzalez. So what will be the answer for this? So we are having a image with 100 lines and 1000 pixels per line. Each pixel can take 256 different values. So total amount of bits. So how many pixels? Total number of pixels? Total pixels are 10 raised to power 5. And number of bits for each pixel? Number of bits for each pixel is 8 because there are only 256 levels. So 8 into 10 to the power 5 bits to be needed to store that image. So consider an imaging system, an object surface which has following illumination and reflectance range. So the illumination range goes from 1 to 100 and reflectance range goes from 0.5 to 1. So remember our simple photometric model. So our fxy is simple multiplication of ixy and rxy. So the range of fxy will be from, so this range will be from 0.5 to 100. Now the question says that the acquired image is stored as grayscale with 8 bits per pixel. Okay, with 8 bits per pixel. So that means our intensity values range will be from 0 to 255. We are storing only positive values. Now an intensity value of say 25 at any location on the surface will get stored as what intensity value? So a value of 25 from this range will get stored to what intensity level in this range? Mhm. Hmm? So you need to have a linear mapping between this range to this range. So from 0.5 has to map to 0 and 100 should get mapped to 125 and intermediate values in between should get mapped to intermediate levels between 0 to 255. So what should be the mapping function? So let us denote this, let us say as x and this as y. So what should be the function? So you can see it as a simple, so let us say this is x and this is y. So 0, sorry. So 0.5 should get mapped to 0, whereas 100 should get mapped to, sorry, 100 should get mapped to 255. So what is the straight line equation? So any values here, any value here to 25 will get mapped to a particular value here, and then we have to quantize it to. So we have different levels 0, 1, 2, 3, 4, 5, 6 to 255. So what is the equation here? Hmm? So how do you get the equation of straight line here? So y minus 0. Hmm? Or you can basically y minus 0.5. Hmm. Maybe I'll do it the other way. To 55 minus 0 upon 100 minus 0.5 into x minus 0.5. So this is the slope of the line. So replace x by 25 here. So it gets around 62.8. So it gets rounded off to. So the intensity value that will be uh, stored will be something around 63, I think. So you can do the calculation.